Good afternoon, everybody. Hey there. Welcome to this session. I'm Zev, a CDO for Communication Intelligence at Very. I'm going to talk to you today about a unique type of big data repository that we've been constructing in the last year or so. First, a spoiler alert. I've been dealing with big data from the time it was called data warehousing, right? That's around 2005, 2006. And, new technologies come by and new people invent new stuff. And then at the end of the day, you realize, well, there's no black magic. And that's really sad, right? When the magic is gone, you feel like someone is taking it from you. By the end of the day, I'm going to present a solution for the problem of collecting huge amounts of data for cyber forensics. So by the end of this session, you'll have a working solution in mind. So that's the first spoiler alert. Second, I'm a big fan of engineering. So as said earlier, there won't be any black magic around here. Sorry. But big data is a really, really good toolbox. And this means that the problems we're dealing with are still very interesting and hard to solve. So in a nutshell, what am I going to talk about? I'm going to claim that not all petabytes are the same. It makes a really big difference if you are creating a petabyte out of images, blogs, text, videos, right? Or if you try to take really, really small things like gene sequences and make a petabyte out of those. And in our specific case for cyber forensics, we are collecting net flows. Net flows are the tiny bits of metadata that you get out of a single TCP connection. Something like who's connecting who, how many bytes were delivered in each direction, and when, supposedly. And they weigh about 100 bytes each. So while it's really common those days to see a petabyte worth of big data repository, even tens of petabytes, it's not that unique anymore. Seeing a petabyte that is constructed out of tiny bits of 100 bytes each, that's unique, and presenting a new set of engineering tasks, and that's what I'm going to talk about today. First thing first, who cares about net flows, right? So we're going to do a 2-slide crash course for cyber forensics, and it's good that I'm coming after the RSA lecture, so, right? It's a good thing. As said, NetFlow is a very small metadata piece associated with a single TCP or UDP connection. It records things like the source, the destination, the time, how much data was delivered in each direction, the protocol, some flags. There is a huge amount of those, approximately 15K for every gigabit. And each and every one of those contain a really, really small piece of valuable information. However, still, when collecting them all, we can do really neat stuff. First thing to understand is that net flows are, in fact, the only evidential part you have in hand when doing cyber analysis. And because of that, and for many other reasons, they are used quite extensively for intrusion detection, for detecting command and control channels for APTs, for detecting botnets, we're going to have that in slide, and for doing link analysis at the network domain. So here's a nice diagram about what is an APT. We got an attacked organization in the green on the right side. We got the attacking organization, and it is an APT, an advanced persistent threat, is much like a military campaign. Okay, so the attacker gathers intelligence about the target, and then it builds a dedicated set of tools, defines the exploit path, defines the way to get in, and eventually injects those exploit tools or exploitation tools into the target organization. As soon as you got an initial foothold within the target organization, this small piece of malware is going to open a command and control channel, basically ET called home. Okay, I'm in, what do you want me to do? Do we need to go to the Active Directory? Do we need to look for the Exchange server? Are we looking for files? Do we need to download a new and more sophisticated piece of software? Okay, so we need a command and control center and a command and control protocol. And finally, assuming that all tools are in, the campaign is starting to bear fruit, the attacker would like to get a report back, and then we're going to see data being exfiliated back to the attacker. If you consider the 4 steps of this very, very high-level diagram of an APT, you can say that an IDS, an intrusion detection system, is going to try and stop the first phase, and then antivirus software of various sorts is going to try and detect malware files and hence detect the exploitation tools. Eventually, CNC, command and control detection tools, are going to try and find anomalies within outbound communication and look for the command and control centers. And eventually, if you're deploying a DLP, a data leakage prevention tool, you might like to go and look for your assets on the gateway on the way out and hence know that you've been compromised. In relevance to our case, net flows are really valuable for IDS, for CNC detection, and not so much for antivirus and DLP cases. Another part of our crash course to cyber attacks is botnet. Who here heard about botnets? Okay, around 50%, that's good. Essentially, a botnet is a way to make easy money. Not all attacks are being done against national security agencies or again national utilities or resources. Actually, most of those are being done in order to get monetary value. How do you do that? Well, you got a bad guy marked at number 1 here, and this guy he's compromising a very, very large set of devices, mostly desktops and mobile devices of you and I. As soon as those devices being compromised, like we said earlier, they go home and they start being robots, or they start accepting commands, start accepting missions and tasks for this operator. And this essentially allows the operator to sell bandwidth and sell free CPU power to the mafia, right? To whoever wants to make use of it. Usually spam, usually credit card fraud. That's all being done by leveraging botnets. The nice thing about botnets is that they have command and control centers, right? If I want to lease my botnet to somebody to allow him to send millions and millions of email, my bots have to accept a new campaign, right? And I have to deliver this campaign to the robots and to tell them what to do. This means that they have an open CNC command and control channel against their servers, and this makes it detectable, at least in retrospect, by tracking net flows. That's the idea. Okay, so this was 2 motivations for why we collect net flows in the first place. A short game of numbers. How many of those do we have? So that's my favorite slide. Suppose I'm a small-scale ISP, and a small-scale ISP might have something like 100 gigabit per second as at the core network. And each of those gigabits are generating approximately 15K new net flows. And suppose, right, well, let's not suppose, there are about 86,000 seconds each day, and suppose I want to retain those for 90 days, I'm getting to approximately 10 to the power of 13, and assuming 100 bytes per each, so that's a terabyte. That's a petabyte, sorry. So that was easy. In practice, 100 gigabps networks, that's not that much. We're seeing terabit networks, and this growing fast, right? Many people talked about that today. So a petabyte is not that much, and we've constructed those out of units of 100 bytes. And that's simply devastating. Querying for images or for movies, that's one thing, but looking for really the needle in the haystack, looking for a 100 byte record within a petabyte, that's going to be a different challenge. Oh, sorry for that. How do we do that? We construct a dedicated repository, and when we set to do that, well, a disclaimer first. We looked for something ready-made. Nobody likes creating a big data repository from scratch. That's not that much fun. tons of engineering, tons of QA, not so much fun. We couldn't find those. And as we started looking for off-the-shelf solutions, we have also sharpened the messages or the challenges we would like to face. The first one is input scalability. We've played with the numbers a slide ago, and you see that we need millions and millions of new flows to be inserted into this repository each second. I know all big data repositories, distributed columnar databases, Hadoop and stuff, they talk about infinite ingest capabilities. That's true if you've got non-structured data with large chunks. When you want this data to be queryable eventually, that's not that true. We wanted unlimited retention. Okay, so we wanted to disconnect the relation between how much data is coming in each second and for how long do I want to retain it. Why shouldn't I store data for 2 years? Who cares? And I wanted a query eventually for a period of 1 week that happened to be 1 year in the past to take the same time for processing as the time required for processing 1 week from the previous month. So this is what I'm talking about. We're talking about decoupling. And we wanted to balance batch and interactive queries. Things like botnet detection, they need large-scale, network-wide phenomena discovery, and this is really the case for MapReduce task, batch processing. Let's take tons of terabyte of data, number crunch over the night, and see what happens. On the other hand, things like IDS and anomaly detection, they need interactive response, and we needed a system to do both. We wanted to have cheap storage. Our customers at Variant are not huge IT farms. Actually, they're not IT experts anyway. And storage, well, it's expensive. And it doesn't interest them so much. So we wanted to be able to do that at cheap storage costs. We wanted to allow simple, select where queries, as well as aggregative queries. Let's do trend lines. Let's do group by, sum, min, max, average, right? Standard deviation and stuff. And we want to do even more complex thing eventually. And last but not least, we wanted to create a very, very low footprint or slim footprint kind of solution, which does not require a lot of maintenance. How many of you have deployed a large-scale Hadoop cluster, let's say 100 nodes? Okay. Can any of you say it's easy to do? No one. So that's the point. During the early stages of our exploration, we got to speak to Katzir, for instance, saying, yeah, sure, you can deploy a 500-node data center and it will do the job for you. And we said, guys, our customers are intelligence officers. They don't know nothing about IT. And maintaining a 500-node cluster, that's a really daunting task. Okay, so we needed something else. I would like to focus some more over the problem of interactive versus batch. And this is where some of the black magic gets to disappear, right? If you want to get interactive query, that's easy. You should add indexes, right? If you got the right index, you can zoom into the right piece of data. They teach us that on the, second semester of the bachelor degree, right? Data structure is something, whatever. Introduction to data structures, yeah, go index. And it's true. It provides you with interactive queries. Point is that when you have tons of data, there is also a lot of overhead, right? Indexes cost storage. Indexes limit your ability to scale, and hence limit our ability to retain data over time. And eventually, if you're going to do batch processing, they're really not useful at all. So, here comes the first freak of big data toolbox and say, sharding, let's shard. Sharding is good, right? Indexes get local, everything gets smaller, everything gets controllable, so that's cool. It's not nearly good enough. And essentially, no solution will going to give you sub-second responses for interactive queries together with a very compact, very elegant way of doing batch processing. So it's all about choosing your work point or your workload. In our specific decision, we kind of leaned towards a compromise. We want interactive queries to return in, let's say, seconds or tens of seconds. That's the walk point that we chose. And on the other hand, allow very large, very complex batch processing to happen overnight without the scalability issues and the storage overheads associated with indexes. How do we do that, right? So trick number one, compression, right? We compress everything and we do it well. It takes less volume, less cost, less footprint. Processing is going to be faster. The oldest trick in the book. Second is sharding. Sharding is good. I like sharding. So I know I made fun of sharding 2 minutes ago, but I like sharding. Sharding is a good thing. We detach inges from query, and you'll see that in a minute. We use commodity hardware. And finally, to get us back to the familiar and loved ecosystem, we provided an HDFS interface to this whole thing. In a nutshell, we created a file-based database. File-based databases are, well, I think not very popular. There are very few projects that deal with file-based databases. The idea is that we have writers on the left, readers on the right. Writers are totally detached from readers, and they create simple, detachable databases. Each and every file they create is a self-encapsulated database that is fully self-sustained, really. It got all the metadata required to describe it, all the mechanics needed to query it, etc. Essentially, each of these files is something like a shard. Now, the secret sauce lies in the way you compress those files and in the way you are able to eliminate shards upon query. That is, if I got 100 million files and I'm going to touch in each and every one of those, well, this is going to be very slow. But if I've got some kind of a magic trick and I can query only 10 out of those, well, that's going to be very, very fast. Considering that I also said I'm not going to construct a global index, we're going to look for a compromise again. Essentially, when looking for file-based database, performance is measured by the number of file shards each CPU core can process per second. That's the trick, right? We got a query. All readers are trying to answer the question, fetching database shards from the storage as fast as they can, and doing that independently. So what did we get? We got scalability because each and every file is independent. We detached readers from writers. We solved the issue of retention period. A week is a week, no matter how deep is it within the storage. We reduced footprint by compression, and we allowed very good scalability because of scalability of writers. And we allowed batch processing because of the lack of global indexes. That's a trick, right? A little bit more details on our specific case. This is general file-based database architecture. So a little bit of our secret sauce. A file, well, that's still quite general, but a file is usually built out of 3 parts. The manifest, describing the structure of the table, structure of the data within the file. What do you need to do in order to look for it? Minimum values, maximum values, a little bit of metadata about the file itself. The index structure is indexing the data within the shard, and eventually the content itself. Processing query means parsing it, inserting it into a queue for parallelism, eliminating shards, that is, eliminating the shards that you don't need for the specific query, processing shards repeatedly by the multiple cores, and eventually aggregating the results and pushing those back to the customer. One note, for a given system, I/O resources are determined. The number of cores are also determined. What we can do is either compress data better to allow more shards to fit into a given terabyte, or we can improve elimination process. That is, require less shards per specific query. And we're doing both. Well, compression, I put this slide and I thought, well, I cannot say much about compression. Fact is, general purpose compression produces something like 3 to 1. There are papers describing net flow compression which show that the limit of compressing a single flow is about 5 to 1. And without saying how much, I'll say we're doing much, much, much better. And we do that by understanding the nature of the data. You can think of it as like compressing MPEGs, right? MPEG compress about 30 to 1. Question is how? Well, the compression algorithm is aware of the fact that this is a movie. And we're doing the same thing. We know it's a net flow. We know the way IP addresses distribute. We know the way timestamps distribute. Okay? We know what the queries that are going to be asked look like. And this allows us to tune entropy in a way that is going in our favor. We're using Bloom filters for elimination of shards. A Bloom filter is a nice structure. It does not make false negatives. That is, if a shard was eliminated, it is unneeded in this case, but it creates a controllable amount of false positive. That is, if you invest more space in the Bloom filter, you'll get less false positives, and you can find your own working point. You know, how much space do you want to invest, and how much benefit are you getting out of it? Process of elimination, really fast. We get a database, and the query goes to the database. First, by the first level of Bloom filter, collection number 3 is being eliminated. Collections number 1 and 2 are relevant, and a secondary level of Bloom filtering is applied. Immediately, we know that some of the shards are irrelevant, where we got shard 1, 3, and 2 over here that seems to be relevant. And then we saw that this one over here was a false positive. That's the trick of elimination and Bloom filters. Results so far. Well, this is a work in progress. We're doing it for a year, and we expect to finish in a few months. But what we've got so far is a multi-petabyte repository with little under 10 commodity servers. We got to easily millions of NetFlow inserts per node per second. This stopped being a barrier long ago. We managed to create linear scalability for both readers and writers. Managed to create industry-leading compression. That is, off-the-shelf solution that we found during the exploration phase got a little better than 2 to 1, something like 2.5 to 1, and we're doing much, much better. Can't state the numbers, sorry. Query performance in the work point that we wanted them to be, that is tens of seconds for sketching petabyte worth of data. And eventually we created an HDFS interface that allows us to do MapReduce on top of all of this. That is for me, unless you've got any questions.